Welcome to Softly Curious. Tonight we begin not with speculation, not with distant parallel realities, but with something more grounded and more quietly astonishing: the limits of what we can actually see. Before we ask whether other universes might exist, we must first understand the boundary of this one, not philosophically, but physically. The universe we speak about in science is often described with a careful qualifier. It is not simply the universe, but the observable universe, a phrase that carries within it both humility and precision. It reminds us that what we measure is defined not by imagination, but by light, time, and expansion. Light travels at a finite speed, approximately 299,792 kilometers per second. And that number is not merely a detail about illumination. It is a structural rule embedded in space-time itself. According to Einstein's theory of relativity, nothing carrying information can travel faster than light in a vacuum. This speed limit shapes everything we know about the cosmos. It means that when we look outward, we are not seeing things as they are now, but as they were when their light began its journey toward us. Distance becomes history. The farther we look, the further back in time we see. The moon appears as it was about 1 second ago. The sun is seen 8 minutes in the past. The nearest stars reveal themselves as they were years ago, and distant galaxies show us light that left them billions of years before the Earth formed complex life. The night sky is not a snapshot of the present. It is a layered archive. Every photon carries a timestamp. The age of the universe is currently estimated at about 13.8 billion years. This number is not arbitrary, nor is it based on a single measurement. It emerges from several independent lines of evidence that converge with remarkable agreement. One method involves measuring how fast the universe is expanding today, a value known as the Hubble constant. Another examines the cooling pattern of the cosmic microwave background radiation. A third analyzes the ages of the oldest known stars and globular clusters. When these measurements are combined, they describe a coherent timeline stretching back nearly 14 billion years. If the universe has existed for 13.8 billion years, then light has had that much time to travel. One might expect, therefore, that the farthest objects we could see would lie 13.8 billion light-years away. But the observable universe is much larger than that. Its current diameter is estimated at approximately 93 billion light-years. This number can seem confusing at first, but it becomes clearer when expansion is understood properly. In 1929, Edwin Hubble observed that distant galaxies exhibit a redshift in their spectral lines. This redshift indicated that they were moving away from us, and more distant galaxies were receding faster. This relationship between distance and velocity became known as Hubble's law. The implication was profound. The universe is expanding. Space itself is stretching, increasing the distances between galaxies. Earlier, the Belgian physicist and priest Georges Lemaître had proposed that the universe began in a much denser, hotter state and expanded from there. He referred to this initial condition as a primeval atom. Hubble's observations provided strong empirical support for this expanding model. Importantly, the expansion does not describe galaxies flying outward from a central explosion into empty space. Instead, space itself is expanding everywhere. A common analogy is dots drawn on the surface of a balloon. As the balloon inflates, each dot sees all others moving away, yet there is no center on the surface itself. Because space expands while light travels, the distance between us and a distant galaxy increases during the photon's journey. A galaxy that emitted light 13 billion years ago may now be tens of billions of light years away due to continued expansion. This is why the observable universe can be so much larger than the simple product of light speed and age. Expansion modifies the scale while light is in transit. One of the most powerful confirmations of the Big Bang model and cosmic expansion came from the discovery of the cosmic microwave background radiation, often abbreviated as the CMB. In 1965, Arno Penzias and Robert Wilson detected a persistent microwave signal using a horn antenna in New Jersey. Initially, they considered the possibility of instrument noise or interference. Before that epoch, the universe was a dense plasma of charged particles. Photons could not travel freely because they constantly scattered off electrons and protons. As the universe expanded, it cooled. Eventually, protons and electrons combined to form neutral hydrogen atoms in a process called recombination. At that moment, light was able to travel without constant scattering. The universe became transparent. The photons released then have been traveling ever since. Today, that radiation has cooled to about 2.7 Kelvin, just above absolute zero. Its wavelength has stretched into the microwave range due to cosmic expansion. It is remarkably uniform, but not perfectly so. Temperature variations of about 1 part in 100,000 exist across the sky. These tiny fluctuations are not random imperfections. They are the seeds of cosmic structure. Slightly denser regions eventually collapsed under gravity to form stars, galaxies, and clusters. Satellites such as COBE, WMAP, and the European Space Agency's Planck mission have mapped the CMB with extraordinary precision. The Planck satellite, in particular, provided detailed measurements of temperature and polarization patterns across the entire sky. From this data, scientists refined estimates of the universe's age, composition, and geometry. The results indicate that ordinary matter accounts for about 5% of the universe's total energy content. Dark matter contributes roughly 27%, and dark energy makes up about 68%. Dark matter does not emit light, but its gravitational effects are visible. It influences the rotation speeds of galaxies and the motion of galaxy clusters. Dark energy, on the other hand, is associated with the accelerated expansion of space. Its discovery in the late 1990s came from observations of distant Type Ia supernova, which revealed that the expansion of the universe is speeding up rather than slowing down under gravity. This acceleration has consequences for the observable universe. Over immense spans of time, distant galaxies will recede beyond our cosmic horizon. Their light will become so redshifted and faint that it can no longer reach us. The observable universe is not a fixed sphere. It evolves as the universe expands. The cosmic horizon marks the maximum distance from which light has had time to reach us since the beginning of cosmic expansion. Beyond that boundary, there may be more galaxies, more matter, more structure, but their light has not yet arrived. The horizon is defined by timing, not by a physical barrier. Any observer in any galaxy would see their own observable sphere, defined by their own horizon. No point in space is privileged. On large scales, the universe appears homogeneous and isotropic, a concept known as the cosmological principle. This principle is supported by observations of large-scale galaxy distribution and the near uniformity of the CMB. Current measurements suggest that the universe is geometrically very close to flat. This flatness means that the total energy density is extremely close to a critical value predicted by general relativity. If the density were much higher, the universe would eventually collapse. If much lower, it would expand too rapidly for structure to form as it has. Instead, the measured value lies strikingly close to this balance. Within the observable universe, astronomers have mapped vast structures such as the Sloan Great Wall and immense galaxy filaments forming a network often described as the cosmic web. Gravitational lensing allows scientists to infer the presence of dark matter by observing how massive objects bend the path of background light. Even subtle polarization patterns in the CMB encode information about conditions in the early universe. All of this information comes from within the observable boundary. The observable universe is not synonymous with the total universe. It is the region of spacetime that has had enough time to communicate with us through light. It is defined by 13.8 billion years of expansion and by the finite speed at which information travels. Before we consider what might exist beyond our horizon, it helps to recognize how much has already been measured within it. Astronomers have mapped the recession of galaxies through redshift surveys, studied the faint glow of the cosmic microwave background, observed distant supernova to detect accelerated expansion, and used gravitational lensing to reveal the presence of dark matter. Together, these observations describe a universe that began in a hot and dense state, expanded and cooled over billions of years, formed structure from tiny early fluctuations, and now continues to stretch under the influence of dark energy. The observable universe is not an abstract idea, but a clearly defined region shaped by two limits: a finite age of about 13.8 billion years, and the fixed speed at which light travels. Everything we know about cosmic structure lies within this expanding sphere of visibility, yet the existence of a horizon suggests that what we see may be only part of a much larger reality. Now we move carefully into a tension hidden within the observable universe itself. Up to this point, the measurements appear calm and consistent: expansion, background radiation, large-scale structure. Yet when cosmologists examined those measurements more closely, two quiet problems emerged. They were not dramatic contradictions, but subtle mismatches between what the early universe should have looked like and what we actually observe. These are known as the horizon problem and the flatness problem, and together they reshaped modern cosmology. The horizon problem begins with something simple. The cosmic microwave background is almost perfectly uniform in temperature. No matter where we look in the sky, the radiation measures about 2.7 Kelvin, with only tiny fluctuations. The puzzle is that distant regions of the early universe appear to have had the same temperature, even though they were too far apart to have ever exchanged information or energy at the speed of light. If two regions were never in causal contact, how did they end up so precisely synchronized? According to simple expansion models, there was not enough time for light to travel between them and equalize their temperatures before the CMB was released. The flatness problem is more mathematical, but equally intriguing. Observations, especially from the Planck satellite, indicate that the geometry of the universe is extremely close to flat. In cosmological terms, this means the total energy density is very close to a critical value. But in the early universe, any tiny deviation from this critical density would have grown dramatically over time. If the density had been slightly higher, the universe would have quickly collapsed back on itself. If slightly lower, it would have expanded too rapidly for galaxies to form. The fact that it remains so finely balanced suggests that the initial conditions were extraordinarily precise. These two problems are not flaws in the data. They are consequences of taking the data seriously. The uniformity of the CMB and the near-perfect flatness of space are both measured facts. The question is not whether they exist, but why they exist. Why is the universe so smooth on large scales? Why is its geometry so delicately balanced? In the early 1980s, physicist Alan Guth proposed a solution that would fundamentally alter cosmology. He suggested that the universe underwent a brief period of extremely rapid expansion very early in its history, long before the formation of atoms or galaxies. This phase is known as cosmic inflation. According to the theory, within a tiny fraction of a second, around 10 to 35 seconds after the beginning, space expanded exponentially. Not linearly, not gradually, but at an accelerating rate that stretched space by an enormous factor in an unimaginably short time. This rapid expansion changes the horizon problem in a simple way. If the universe was once much smaller and closely connected, then regions that now appear far apart may originally have been near each other. In that early state, energy and radiation could mix and reach the same temperature. When inflation stretched space at an extraordinary rate, those once neighboring regions were pushed far beyond each other's horizons. The smoothness we see today in the cosmic microwave background would then reflect that earlier connected phase, rather than a coincidence across vast distances. Inflation also offers a solution to the flatness problem. Exponential expansion naturally drives space toward geometric flatness. As space stretches, any initial curvature becomes diluted. What once required extremely precise initial conditions becomes far less improbable. The near-perfect flatness we measure today is not a coincidence, but a consequence of that early expansion. At the same time, inflation does not erase small irregularities. It gives them structure. Tiny quantum fluctuations in the very early universe-minute variations in energy density were stretched to cosmic scales during inflation. These amplified fluctuations later became the seeds of galaxies and clusters. The slight temperature variations observed in the cosmic microwave background by the Planck satellite correspond closely to these early perturbations. Inflation does not replace the Big Bang model. It refines it. It explains why the universe appears so uniform and geometrically balanced while still allowing for the subtle imperfections that form structure. The horizon and flatness problems are not signs that the model failed, but signs that something dramatic occurred in the universe's first fraction of a second. In that brief interval, space expanded at an extraordinary rate, quietly setting the stage for everything that followed. Cosmic inflation was first proposed as a solution to specific problems in early cosmology. But as the mathematics matured, it began to suggest something far larger than a brief episode of rapid expansion. What started as an explanation for uniformity gradually opened into a possibility that inflation may not have been a single event that turned on and then cleanly turned off everywhere at once. Instead, it may be a process that continues in parts of space even now, quietly generating new regions of expansion beyond anything we can observe. In its simplest form, inflation describes a moment in the early universe when space expanded at an exponential rate. Not steadily, not gradually, but explosively fast. Within a tiny fraction of a second, around 10 to 35 seconds after the beginning, space stretched by an enormous factor. Distances between points doubled again and again in rapid succession. This expansion was driven not by matter in the usual sense, but by energy stored in a field permeating space itself. That field is often described in terms of vacuum energy. The word vacuum can be misleading because it suggests emptiness. In physics, however, a vacuum is not truly empty. Even in the absence of particles, space can contain energy. Quantum field theory allows for fields that have energy even when no particles are present. During inflation, a high-energy state of such a field dominated the dynamics of the universe. Originally, inflation was imagined as a temporary phase. The field would begin in a high-energy state, drive rapid expansion, and then decay into a lower-energy state. When it decayed, inflation would end, and the familiar hot Big Bang evolution would begin. Radiation would fill space, particles would form, and cosmic history would proceed. But as theorists examined the equations more closely, a subtle possibility emerged. What if the decay of this high-energy state does not happen everywhere at once? What if some regions of space transition out of inflation, while others remain in the high-energy state and continue expanding? This idea was developed most prominently by physicist Andre Linde. In his model of eternal inflation, the process becomes self-sustaining. While certain regions exit inflation and form what we would recognize as universes like our own, other regions continue expanding exponentially. Because expansion itself creates more space, there is always room for inflation to continue somewhere. The key insight is mathematical. Exponential expansion can outpace decay. Even if parts of space transition out of the inflationary phase, the overall volume of inflating space can still grow. Regions that remain in the high-energy vacuum expand so rapidly that they compensate for and exceed the regions that have already transitioned. This means inflation does not simply happen once and end. It becomes eternal, at least into the future. In this picture, our observable universe is just one region where inflation has locally ended. In that region, the vacuum energy dropped to a lower state, reheating space and producing the particles and radiation that would later form stars and galaxies. But beyond our horizon, inflation may still be occurring, generating new regions continuously. To describe these regions, cosmologists often use the metaphor of bubbles. When a local area exits inflation, it forms a kind of bubble universe within a larger inflating background. The bubble is not expanding into empty space like a soap bubble in air. Rather, it is a region where the vacuum energy has shifted to a different state, and normal cosmic evolution begins inside it. The bubble metaphor is useful but imperfect. What is really happening is a transition between energy states of a field that fills space. When the field decays in a localized region, that region effectively becomes a new expanding universe. Surrounding it, the inflating background continues to stretch at an extraordinary rate. Because the background expansion is exponential, the distance between these bubble regions grows extremely quickly. Even if many such bubbles form, they are typically carried away from each other, faster than light can travel between them. This does not violate relativity, because it is space itself that is expanding, not objects moving through space faster than light. In eternal inflation, the process has no global end. There is no moment when all of space simultaneously stops inflating. Instead, inflation ends locally repeatedly in different regions. Each local ending produces a new cosmic domain. An important consequence of this framework is that different bubble regions may settle into different physical conditions. When the vacuum energy decays, it does not necessarily decay in exactly the same way everywhere. The energy landscape of the field may allow multiple possible lower energy states. Each bubble could correspond to a different minimum of that landscape. If that is true, then different bubbles could have different physical constants. The strength of forces, the values of certain parameters, or the properties of particles might vary from one region to another. Within our bubble, we measure specific values for quantities such as the cosmological constant or coupling strengths. In another bubble, those values might be different. This does not require exotic assumptions beyond the mathematics of fields with multiple stable states. In many physical systems, energy landscapes contain more than one minimum. A simple example is water. Under different conditions, it can settle into ice, liquid, or vapor. The underlying substance is the same, but its phase differs depending on energy conditions. In eternal inflation, the vacuum field could behave similarly, though on a far more abstract and fundamental level. Different regions could freeze into different states as inflation ends locally. Each state would define a different set of physical properties. The mathematics behind eternal inflation relies on probabilistic processes within quantum fields. Small fluctuations in the field can determine whether a region decays to a lower energy state or remains inflating. Because expansion is so rapid, regions that remain inflating can grow in volume faster than regions that decay. The result is a cosmic structure that, on the largest scales, resembles a branching process. Not branching in the quantum many-world sense, but branching in terms of spatial domains emerging from an inflating background. The global picture is one of continuous generation. This model also implies that inflation is not a rare event confined to the distant past. Instead, it is an ongoing process beyond our observable horizon. While our region has cooled and formed galaxies, other regions may still be in an inflationary phase, expanding exponentially with vacuum energy dominating their dynamics. Because these regions are separated by enormous distances and expanding space, we have no direct observational access to them. They lie beyond our cosmic horizon. The exponential expansion ensures that even if bubble universes form near each other, they are rapidly driven apart. In this framework, the observable universe becomes one local outcome of a much larger process. The uniformity we observe within our horizon is explained by early inflation, but inflation itself may be part of a broader, never-ending cosmic structure. The idea of eternal inflation does not arise from philosophical speculation. It emerges from extending the mathematics of inflationary models. When the equations are allowed to evolve without forcing a global end condition, they naturally permit a self-reproducing structure. The concept of vacuum energy plays a central role here. As long as regions remain trapped in a high-energy state, expansion continues. If the decay rate of that state is slow compared to the rate of exponential growth, then inflating space increases overall. Even if decays occur everywhere locally, the total inflating volume can still grow without bound. This leads to a striking implication. The process has no obvious global beginning or end within its own framework. Individual bubble universes have beginnings, like ours, but the larger inflating structure may persist indefinitely. In such a picture, our universe is not the entire story of cosmic expansion. It is one stabilized region within a much larger inflating background. Its physical laws and constants may reflect the specific way the vacuum field settled in our domain. Eternal inflation changes the picture. The rapid expansion that solved the early cosmological problems may not have happened only once. It may have ended in our region while continuing elsewhere. In this view, our observable universe is a local area where inflation stopped and normal cosmic evolution began. Beyond our horizon, inflation could still be expanding space and creating new regions. If those regions settle into different energy states, they may develop different physical conditions. This possibility does not come from imagination. It follows from extending the mathematics of inflation itself. When inflation ends in a particular region, the vacuum energy does not simply disappear. It settles into a lower state. The exact value of that remaining energy matters enormously. In our universe, this leftover energy appears as the cosmological constant, a small but measurable driver of accelerated expansion. Its value is extremely tiny compared to what many theoretical calculations predict, yet it is not zero. If it were significantly larger, space would expand so rapidly that galaxies could never form. If it were negative and large in magnitude, the universe might quickly recollapse. The small positive value we measure allows structure to exist. The cosmological constant is only one example of a physical parameter that could, in principle, vary from region to region. Another is the strength of the strong nuclear force. This force binds protons and neutrons together inside atomic nuclei. If it were slightly weaker, stable nuclei might not form beyond hydrogen. If slightly stronger, nuclear reactions inside stars would proceed very differently. The balance that allows carbon and oxygen to exist depends delicately on this force's strength. The electromagnetic force also plays a central role in shaping matter. It governs how electrons bind to atomic nuclei and determines the structure of atoms and molecules. If its strength were altered even modestly, chemistry as we know it would change dramatically. Atoms might not hold together in stable configurations. Complex molecules, including those necessary for stars, planets, and potentially life, could be impossible. In eternal inflation scenarios, different regions could settle into different energy minima. This idea becomes more structured in certain approaches to high-energy physics, particularly in versions of string theory. Within these frameworks, the underlying equations allow for a vast number of possible vacuum states. Each vacuum corresponds to a different set of physical constants and particle properties. Physicist Leonard Susskind described this idea as a landscape of possibilities. Instead of a single unique vacuum state, the theory permits many stable or metastable configurations. Each configuration defines a different version of low-energy physics. The number of possible states is often estimated to be extraordinarily large, sometimes quoted as around 10,500. This number is not precise, but it conveys the scale of the theoretical space. If inflation generates many separate regions, and if each region can settle into a different vacuum state from this landscape, then different domains could naturally exhibit different physical constants. Our universe would be one realization among many possible configurations. Its specific values for the cosmological constant and force strengths would reflect the particular minimum into which its vacuum energy settled. In this framework, the multiverse does not arise from splitting timelines or branching decisions. It arises from variations in fundamental physical parameters across different regions of spacetime. Each bubble universe could obey the same underlying laws of field theory, yet display different constants and low energy behavior. The differences would not be random fantasies, but outcomes permitted by the structure of the theoretical landscape itself. When physics entered the 20th century, it did not gently expand its boundaries, it fractured them. Classical mechanics had described a world in which objects possessed definite properties at all times. A planet had a position and velocity whether or not anyone observed it. A ball followed a trajectory determined by forces. The universe, in that picture, behaved like a vast but understandable machine. Then experiments at atomic scales began to suggest something far less intuitive. At very small scales, nature did not behave like solid objects moving through clear space. It behaved like probabilities. At the heart of quantum mechanics lies the wave function. The wave function is not a physical wave in the ordinary sense, like water ripples or sound vibrations. It is a mathematical object that encodes information about a system. For a particle such as an electron, the wave function describes the probabilities of finding that particle in different positions or states. It does not assign a single definite location prior to measurement. Instead, it provides a distribution of possibilities. This leads to one of the central features of quantum theory, superposition. A system in superposition is not in one definite state. It is described as being in multiple possible states simultaneously, at least mathematically. An electron passing through a double-slit apparatus does not behave as though it went through one slit or the other. The interference pattern observed on the detection screen suggests that the electron's wave function passed through both slits and interfered with itself. The mathematics predicts this precisely, and experiments confirm it repeatedly. It is important to state this carefully. Saying that an electron is in two places at once is shorthand. More precisely, the electron is described by a wave function that assigns non-zero probability amplitudes to multiple positions. Until a measurement is made, the system evolves according to a deterministic equation known as the Schrödinger equation. This equation governs how the wave function changes over time. It is smooth, continuous, and predictable. The difficulty appears when a measurement occurs. When we measure the position of an electron, we do not observe a spread-out distribution. We observe a definite result. The electron appears at a single location. The interference pattern disappears if we try to detect which slit the electron passed through. The wave function, which previously described multiple possibilities, seems to reduce to one outcome. This sudden change is often described as collapse. The measurement problem arises from the tension between these two descriptions. On the one hand, the Schrödinger equation predicts continuous evolution of the wave function. On the other hand, measurements yield discrete, definite outcomes. The theory seems to contain two different kinds of evolution: smooth, deterministic evolution when unobserved, and abrupt, probabilistic collapse when observed. The question is not whether the predictions match experiment. They do. The question is what exactly counts as a measurement, and why it changes the description so radically. Niels Bohr, one of the founders of quantum mechanics, played a central role in shaping what became known as the Copenhagen interpretation. According to this view, the wave function does not represent a physical object in space in the classical sense. Instead, it represents our knowledge or information about the system. The act of measurement is not merely passive observation. It is an interaction between the quantum system and a classical measuring apparatus. After this interaction, the wave function is updated to reflect the observed outcome. In the Copenhagen interpretation, the question, which slit did the electron really go through, is considered misguided if no measurement was performed. The theory does not assign definite properties before observation. Physical quantities acquire definite values only in the context of measurement. The wave function provides probabilities for outcomes, not hidden definite states waiting to be revealed. This interpretation is often summarized with a phrase sometimes attributed to Bohr. Physics concerns what we can say about nature, not necessarily how nature is independent of observation. Whether or not Bohr used those exact words, the sentiment reflects the Copenhagen emphasis. The theory is a tool for predicting measurement outcomes. Asking for more may go beyond what the formalism provides. The measurement problem becomes clearer through a thought experiment proposed by Erwin Schrödinger in 1935. Schrödinger's cat was not meant as a literal experiment, but as a way of illustrating the strange implications of applying quantum superposition to larger systems. In the scenario, a cat is placed in a sealed box along with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers the release of poison and the cat dies. If the atom does not decay, the cat remains alive. Radioactive decay is a quantum process described probabilistically. Before measurement, the atom can be described as being in a superposition of decayed and not decayed states. If the entire system is treated quantum mechanically, the cat becomes entangled with the atom's state. The mathematics would describe the combined system as a superposition of atom decayed, cat dead, and atom not decayed, cat alive. The question Schrödinger posed was not whether cats are literally both alive and dead. It was meant to highlight the difficulty of defining where quantum superposition ends and classical reality begins. If quantum mechanics applies universally, then why do we not observe macroscopic superpositions in everyday life? At what scale does collapse occur, and what physically causes it? In laboratory settings, superposition is routinely observed in microscopic systems. Electrons, photons, and even larger molecules can exhibit interference effects consistent with superposition. Experiments have demonstrated superposition in systems containing thousands of atoms. Yet the everyday world appears classical. Chairs do not exist in overlapping positions. Cats are not observed in ambiguous life states. The Copenhagen interpretation addresses this by drawing a conceptual boundary between quantum systems and classical measuring devices. The measuring apparatus is treated classically, and the quantum system is described probabilistically until measurement. However, this boundary is not precisely defined within the formalism itself. Where exactly does the quantum description give way to classical description? The theory works, but its conceptual foundation invites questions. Another aspect of the measurement problem concerns determinism. The Schrödinger equation evolves deterministically. If the wave function at one moment is known, its future evolution can be calculated precisely. Yet the outcome of a measurement appears inherently probabilistic. Even with complete knowledge of the wave function, one can predict only the probabilities of different results, not the specific outcome that will occur. This probabilistic nature is not due to experimental ignorance in the usual sense. In classical physics, probabilities often reflect incomplete knowledge. In quantum mechanics, the probabilities are fundamental to the theory structure. The electron's position is not merely unknown before measurement. It is not assigned a definite value within the Copenhagen framework. It is worth noting that quantum mechanics has been tested with extraordinary precision. Predictions about atomic spectra, semiconductor behavior, laser operation, and chemical bonding all rely on the wave function formalism. The measurement problem does not arise because the theory fails experimentally. It arises because the theory's mathematical structure and its interpretation do not align seamlessly. One might ask whether the wave function is a real physical entity or simply a calculational tool. In the Copenhagen view, the emphasis remains on prediction. The wave function encodes probabilities. It is not necessarily a physical wave propagating through space in the classical sense. Yet experiments such as interference patterns suggest that something about the wave function has real, observable consequences. The double-slit experiment remains one of the clearest demonstrations of quantum superposition. When electrons are fired one at a time toward two slits, and no attempt is made to detect which slit they pass through, an interference pattern gradually emerges on the screen. This pattern can only be explained if each electron's wave function passes through both slits and interferes with itself. If detectors are placed at the slits to determine the path, the interference pattern disappears. The act of measurement changes the outcome. This is the core of the measurement problem. The formalism of quantum mechanics predicts superposition and interference, yet the act of observation yields definite results. The transition from possibility to actuality is not described by the same smooth equation that governs unobserved evolution. Instead, collapse is introduced as a separate postulate. For Bohr and proponents of the Copenhagen interpretation, this was not necessarily a flaw. It was a recognition that classical language and classical measuring devices are unavoidable when describing experiments. The theory does not describe an objective underlying reality independent of measurement. It describes correlations between preparation procedures and observed outcomes. Whether this stance is satisfying depends on philosophical inclination. Some physicists accept it as a pragmatic solution. Others see the measurement problem as evidence that the theory is incomplete or that its interpretation requires refinement. What is clear is that quantum mechanics introduces a fundamental shift from classical intuition. An electron described by a wave function does not carry a definite position and momentum simultaneously in the classical sense. Instead, it exists in a superposition of possible states, evolving predictably until a measurement forces a definite outcome. The mathematics is precise. The conceptual picture is subtle. In this subtlety lies the opening to deeper questions. If the wave function evolves deterministically according to the Schrödinger equation, and if collapse appears only when measurement occurs, then what exactly constitutes measurement? Is it interaction with a macroscopic object? Is it irreversible amplification? Is it the involvement of consciousness? The Copenhagen interpretation does not assign a special role to consciousness, but it leaves the boundary conceptually open. The measurement problem does not invalidate quantum mechanics. Rather, it reveals that the theory challenges classical assumptions about reality. It asks whether properties exist independently of observation, or whether observation plays a constitutive role in defining them. The formalism remains consistent and experimentally verified, yet its interpretation continues to invite debate. Within the Copenhagen framework, the wave function encodes probabilities rather than definite properties. Superposition describes multiple possible outcomes, and measurement produces a single result. The theory works with remarkable precision, yet the contrast between smooth evolution and sudden collapse remains at its core. But the tension remains. Two types of evolution appear in the same theory: smooth deterministic change and abrupt probabilistic collapse. The measurement problem is not a technical error. It is a conceptual crossroads. And it is precisely at this crossroads that alternative interpretations of quantum mechanics begin to emerge. In the late 1950s, a young physicist named Hugh Everett III proposed a different way of reading the mathematics of quantum mechanics. He did not change the equations. He did not modify the Schrödinger equation or introduce new forces. Instead, He asked a simple question. What if the wave function never collapses at all? What if the mathematical description we already use is complete and universally valid? Everett suggested that the wave function should apply not only to tiny particles, but to everything, including measuring devices and observers. If the Schrödinger equation governs all physical systems, then there is no need to introduce a special collapse rule during measurement. The wave function would continue evolving smoothly and deterministically at all times. The apparent collapse would be replaced by something else. In this view, when a measurement occurs, the combined system of particle and observer becomes entangled. Instead of one outcome being selected, the total wave function contains multiple components, each corresponding to a different possible result. These components no longer interfere with one another in practice, but they remain part of the overall mathematical structure. Each outcome persists within the universal wave function. This interpretation later became known as the many worlds interpretation. The phrase suggests drama, but the core idea is restrained and mathematical. If the wave function describes reality, and if it evolves without collapse, then every outcome allowed by the wave function is realized in some branch of the overall state. Nothing is discarded. No possibility is erased. To understand this more clearly, consider a simple quantum event, such as measuring the spin of an electron. According to standard quantum mechanics, the electron can be in a superposition of spin up and spin down before measurement. In the Copenhagen view, measurement forces the system into one of those states. In Everett's view, the measurement produces a larger superposition. One branch in which the observer records spin up, and another branch in which the observer records spin down. From within each branch, the observer experiences a definite outcome. There is no sense of ambiguity inside a single branch. The splitting is not something consciously perceived. It is a feature of the mathematical structure describing the entire system. Each branch evolves independently after decoherence separates them effectively. Decoherence plays a crucial role in making this picture consistent with everyday experience. When a quantum system interacts with its environment, the different components of its wave function quickly lose the ability to interfere with one another. The environment effectively records the outcome, spreading information into countless degrees of freedom. As a result, the branches become dynamically isolated. They no longer overlap in any observable way. Importantly, this branching does not violate conservation laws. The total energy of the system remains governed by the same Schrödinger equation, and the universal wave function continues to evolve deterministically. The apparent multiplication of outcomes does not create extra energy or duplicate matter in a classical sense. Instead, all outcomes remain contained within a single, evolving quantum state whose components become effectively separated through decoherence. Everett's proposal was controversial at first, and for many years it remained outside the mainstream. Over time, however, it attracted renewed interest because it removes the special role of collapse from quantum theory. In this interpretation, reality does not narrow to one randomly selected outcome. Rather, every allowed possibility continues in its own branch, each internally consistent and dynamically isolated, while the underlying mathematics remains unchanged. When people hear the phrase parallel universes, they often imagine different physical laws or branching timelines. But there is a quieter version of the idea, one that requires no new physics at all. It begins with a simple question: what if space itself is infinite? Modern cosmology does not yet know with certainty whether the universe is spatially infinite. What measurements tell us is that on very large scales, space appears remarkably flat. Observations of the cosmic microwave background, especially from the Planck satellite, suggest that the curvature of the universe is extremely close to zero. A flat universe can be finite, like the surface of a torus, or it can be infinite, extending without boundary. The data allow both possibilities within small margins of uncertainty. If space is finite but unbounded, it could loop back on itself in higher dimensions. In such a geometry, one could in principle travel far enough in one direction and eventually return to the starting point, though the scale would be unimaginably vast. This idea can feel abstract, but it is not mystical. The surface of the Earth is finite, it has no edge. You can walk in a straight line without ever encountering a boundary. If, however, space is truly infinite, then the implications become mathematically interesting. Infinite space does not automatically mean infinite variety. What matters is the number of possible arrangements of matter within a given region. And here we enter the realm of combinatorics. Consider a region of space roughly the size of our observable universe. Cosmologists sometimes refer to such a region as a Hubble volume. It is the portion of space from which light has had time to reach a given observer. Within that volume, there is a finite amount of matter and energy. That means there are only so many ways atoms can be arranged within it. The number of possible atomic configurations is extraordinarily large, but it is not infinite. Given a finite amount of matter distributed among a finite number of quantum states, the total number of distinct arrangements, while vast, remains limited. This is not an assumption. It follows from the mathematics of quantum systems. Now imagine that space extends infinitely, with the same basic laws of physics applying everywhere. If the number of possible arrangements within a Hubble volume is finite, and if there are infinitely many such volumes spread across infinite space, then the same arrangements must eventually repeat. This is not speculation. It is a consequence of the pigeonhole principle applied on a cosmic scale. If you roll a six-sided die infinitely many times, every possible sequence of outcomes will occur not just once, but infinitely many times. If the number of possible outcomes is finite and the number of trials is infinite, repetition is unavoidable. The universe, under these assumptions, behaves similarly. Max Tegmark, a cosmologist and physicist, formalized this idea as what he calls the level I multiverse. In this model, there are no new laws of physics, no altered constants, and no branching timelines. There is only more space beyond what we can see. If space is infinite and statistically uniform on large scales, then distant regions should contain matter arranged in every possible way consistent with our physical laws. Some of those arrangements would differ from ours only slightly. Others would be dramatically different. Given enough distance, there would be regions where galaxies are arranged differently, where stars formed earlier or later, where planetary systems took alternate shapes. And at inconceivably large distances, there would be regions where the atomic configuration matches ours exactly. The distance to the nearest identical Hubble volume, if it exists, would be beyond comprehension. Estimates based on reasonable assumptions suggest numbers like 10 to the power of 10 to the power of 115 meters. Such figures are so enormous that they resist visualization. Yet the precise number matters less than the principle. If the set of possible configurations is finite and the number of trials is infinite, repetition becomes inevitable. It is important to emphasize that this version of parallel universes does not require speculative new physics. It depends only on two conditions: infinite space and uniform laws. If those hold, then somewhere unimaginably far away, there could be another region of space where matter is arranged exactly as it is here. Another Earth, another sky, another configuration of atoms forming identical structures. This idea can feel unsettling, but it is grounded in straightforward probability. Imagine writing a long string of letters using a fixed alphabet. The number of possible combinations of letters in a paragraph is enormous but finite. If you continue writing random paragraphs forever, eventually you will reproduce an earlier paragraph exactly. The more text you generate, the more combinations you explore. Given infinite length, repetition is guaranteed. The same logic applies to atomic arrangements. The alphabet is composed of quantum states. The paragraph is a Hubble volume. Infinite space provides infinite opportunities for rearrangement. One might ask whether infinite space is realistic. Current observations show that the universe appears extremely flat on large scales, and inflationary models suggest that space could extend far beyond what we can observe. We cannot see beyond our cosmic horizon, so we cannot confirm whether space is truly infinite. But if it is flat and unbounded, it may continue without edge. Even if the universe began in a finite state, rapid expansion could have stretched it so extensively that it behaves as effectively infinite. What makes the level I multiverse distinctive is its simplicity. It does not introduce new dimensions or exotic physics. It does not change the laws of nature. It simply extends space beyond our observable region. The laws of gravity, electromagnetism, and nuclear forces remain the same everywhere. What changes from region to region is not the rules, but the arrangement of matter within those rules. If space is infinite and the number of possible atomic arrangements inside a Hubble volume is finite, then repetition becomes unavoidable. This is not mystical. It follows from basic combinatorics. Finite possibilities placed into infinite space must recur. In that sense, repeating realities would not arise from branching timelines or altered laws, but from the quiet mathematics of scale itself. When space is imagined as vast beyond measure, probability becomes more than a tool for predicting dice rolls or particle spins. It becomes a way of thinking about identity itself. In an infinite setting, events with extremely small probabilities are not impossible. They are simply rare. If there are infinitely many trials, even rare events occur somewhere. The question shifts from, can this happen? To, how often does this happen within an infinite landscape? Probability density is the key idea here. In simple terms, probability density describes how likely different outcomes are within a continuous range of possibilities. In quantum mechanics, for example, the square of the wave function gives a probability density for finding a particle in a particular region. In cosmology, similar reasoning can apply when considering how matter might arrange itself across vast regions of space. Some configurations are overwhelmingly common. Others are extremely rare. But in an infinite setting, rarity does not mean absence. This line of reasoning connects to an idea that predates modern cosmology. In the 19th century, the physicist Ludwig Boltzmann studied the statistical behavior of gases. He argued that macroscopic order can arise from microscopic randomness through statistical fluctuations. Given enough time, even unlikely configurations of particles can occur spontaneously. His work laid the foundations for statistical mechanics, where large-scale properties emerge from probabilities at small scales. If we extend Boltzmann's reasoning to the universe as a whole, a striking possibility appears. In an infinite cosmos filled with particles in motion, random fluctuations could occasionally assemble complex structures purely by chance. Most fluctuations would be small and disordered. Very rarely, however, a large fluctuation might briefly produce an organized system. The larger and more specific the structure, the lower its probability. Yet in infinite space or infinite time, even extremely low probability events can occur somewhere. This leads to what is called the Boltzmann brane hypothesis. It is not a prediction, but a consequence of statistical reasoning. If random fluctuations can produce order, then in an extremely large universe, it may be more likely for a single, self-aware brain to briefly form by chance than for an entire structured universe like ours to arise through normal cosmic evolution. The implication is unsettling, but it follows from probability applied at enormous scales. The hypothesis is not meant to describe our reality, but to reveal a tension within cosmological models that rely on infinity and probability. If random, short-lived conscious fluctuations would statistically outnumber stable universes, then such models must explain why we observe a consistent and long-lived cosmos. In this framework, identity becomes a matter of distribution rather than uniqueness. If space is infinite and matter can arrange itself infinitely many ways within a given region, then similar structures may exist elsewhere. Nothing mystical is required here. The reasoning rests on probability density, combinatorics, and statistical mechanics, extending Boltzmann's insight that order can arise from randomness into a cosmic scale. Long before physicists began writing equations about multiple universes, writers were already exploring the idea that reality might branch, divide, or unfold along more than one path. The concept of parallel outcomes did not originate in laboratories or particle accelerators. It first appeared in stories, in philosophical reflections, and in quiet literary experiments that questioned whether a single linear timeline was the only way to imagine existence. One of the clearest early expressions of this idea appears in the short story The Garden of Forking Paths by Jorge Luis Borges. Written in 1941, decades before the many worlds interpretation of quantum mechanics gained attention, Borges imagined a novel in which all possible outcomes of an event occur simultaneously. In his story, time does not split into separate alternatives that cancel each other out. Instead, every possible path exists at once, creating a labyrinth of branching realities. The image is literary rather than scientific, yet the structure is strikingly close to later physical interpretations. Borges did not describe wave functions or decoherence. He described a book that contains every possible version of its narrative. A character chooses one path, but in another strand of time, he chooses differently. The story suggests that reality may not be a straight corridor, but a network of diverging routes. The idea is presented as metaphor, but it reflects a deep intuition that the future is not a single line, but a field of possibilities. This intuition appears again in the works of Philip K. Dick. Writing in the mid-20th century, Dick repeatedly questioned whether the world we experience is the only one that exists. His stories often revolve around characters who discover that their reality is unstable, layered, or partially constructed. In novels such as The Man in the High Castle, alternative histories are not simply imagined. They are treated as coexisting narrative possibilities. Dick's focus was not mathematical branching, but psychological destabilization. He explored what it feels like when certainty dissolves. In these literary explorations, the branching of reality is not derived from physics. It is derived from human experience. Every decision implies an unchosen alternative. Every path taken leaves behind paths not taken. Literature gave form to this feeling long before cosmology gave it equations. The multiverse, in this sense, began as a narrative device, a way of expressing the complexity of choice. Cinema later transformed this narrative device into visual structure. The film Sliding Doors offers a simple but powerful example. The story follows two versions of the same woman's life, diverging at a single moment, whether she catches a train. One timeline unfolds from catching it, the other from missing it. The film does not invoke quantum mechanics or cosmology. It simply places two outcomes side by side, inviting viewers to reflect on how small events can redirect entire futures. The appeal of this structure is immediate. It resonates with everyday imagination. Most people have wondered at some point how life might have unfolded differently if one decision had changed. Sliding Doors does not propose that both realities physically coexist. It dramatizes the emotional weight of contingency. The multiverse here is psychological, not cosmological. A more subtle cinematic exploration appears in Coherence. Set almost entirely during a dinner gathering, the film introduces a passing comet and gradually reveals that parallel versions of the same evening may be overlapping. Characters encounter slightly altered versions of events and possibly of themselves. The film's tone is restrained and unsettling rather than spectacular. It does not rely on grand visual effects. Instead, It builds tension from the idea that multiple possibilities may coexist, separated only by thin boundaries. Coherence draws loosely on quantum language, but it remains a narrative exploration rather than a scientific argument. Its power lies in atmosphere and ambiguity. The branching realities are experienced through confusion and identity shifts rather than through equations. What makes it compelling is not physics, but the unsettling suggestion that small variations in circumstance could produce entirely different interpersonal outcomes. What is striking across these works is that the idea of parallel paths arises naturally from narrative structure itself. Stories depend on choice. Characters face alternatives. Once a decision is made, the unchosen option lingers as a ghost possibility. Literature makes this visible. Film makes it tangible. Neither requires the mathematics of wave functions to generate the concept. This historical sequence matters. The multiverse did not enter culture because of physics alone. The cultural imagination was already primed for it. Borges, Dick, and later filmmakers were exploring branching realities as metaphors for uncertainty, identity, and consequence. When physicists later introduced formal multiverse models, the cultural ground had already been prepared. There is also a deeper psychological layer beneath these narratives. Human cognition naturally constructs counterfactuals. When we reflect on past events, we simulate alternatives. We imagine what might have happened if a conversation had gone differently, or if a decision had been reversed. This capacity for counterfactual thinking is central to planning and learning. It also makes the idea of parallel realities intuitively compelling. Parallel worlds in literature often serve as mirrors. They reflect not cosmic structure, but human longing. They allow characters to confront versions of themselves shaped by different choices. In doing so, they externalize internal conflict. The branching world becomes a metaphor for branching identity. Yet it is important to maintain a clear distinction. The literary multiverse is an expressive device. The scientific multiverse is a theoretical consequence of physical models. They may resemble each other structurally, but their origins differ. Borges' branching garden is a narrative construction. Everett's branching wave function arises from mathematical formalism. The similarity is conceptual, not causal. Recognizing this distinction does not diminish either domain. Instead, it clarifies the relationship. Literature anticipated the structure of branching reality, not because it predicted quantum mechanics, but because it explored the logic of choice and time. Science later provided models in which branching appears as a physical interpretation. In this way, the cultural history of parallel worlds reveals something subtle. The multiverse was not imposed upon culture by physics. It emerged from the human imagination independently. When cosmology and quantum mechanics introduced formal multiverse ideas, they encountered a concept already familiar in art and storytelling. Parallel worlds in literature and film therefore serve two functions. They entertain and provoke reflection, but they also prepare intuition. They make abstract ideas emotionally accessible. When scientific discussions of multiple universes enter public awareness, they find resonance because the narrative structure is already known. The fascination persists because the idea operates on two levels simultaneously. It addresses the structure of reality, and it addresses the structure of regret and possibility. It speaks to cosmology, and it speaks to personal history. This dual appeal ensures that parallel worlds remain compelling across disciplines. By the time physicists began debating inflationary bubbles or branching wave functions, the imaginative groundwork had already been laid. Stories had shown that reality could fork. Films had shown that one evening could contain two outcomes. Literature had explored labyrinths of time decades earlier. The multiverse, then, is not solely a product of equations. It is also a product of narrative intuition. And understanding this cultural lineage helps explain why the scientific versions of parallel worlds resonate so strongly beyond the laboratory. In recent years, the idea of parallel worlds has moved from philosophy and speculative fiction into mainstream entertainment. The multiverse is no longer a quiet literary concept. It has become a central device in blockbuster storytelling. In many popular narratives, alternate versions of characters meet each other. Timelines collide, and realities overlap in visually dramatic ways. These stories are entertaining and imaginative, but they often blur the line between scientific models and narrative freedom. The Marvel multiverse, for example, presents parallel universes as accessible domains that can be visited, crossed, or merged. Characters encounter alternate versions of themselves with different personalities or histories. These versions coexist in separate but reachable realities. The structure is flexible and designed to expand storytelling possibilities. It allows familiar characters to be reinterpreted without abandoning continuity. Similarly, in the animated series Rick and Morty, parallel universes are treated as almost casual destinations. Characters travel between realities, replacing alternate selves or interacting with slightly altered worlds. The show deliberately exaggerates the concept for humor and philosophical satire. Its tone is self-aware and absurd, yet it reinforces the idea that infinite variations of reality are easily accessible. These portrayals are creative, but they do not represent scientific models accurately. In physics, parallel universes, if they exist, are not portrayed as places one can travel between. Another modern trend is the reinterpretation of quantum mechanics in internet culture. The phrase quantum jump is often used to describe personal transformation, manifestation, or shifting into a preferred reality. In physics, however, a quantum jump refers to a discrete transition between energy states in an atom. It has a precise technical meaning. The popular reinterpretation detaches the phrase from its scientific context and assigns it psychological or mystical significance. The NPC theory, circulating online, offers another example. In gaming terminology, a non-player character follows programmed behavior without independent agency. Some online discussions use this metaphor to suggest that certain people are less conscious or less real than others, as though reality contains background figures. This idea has no basis in physics or neuroscience. It reflects social and psychological dynamics rather than cosmological theory. The persistence of these misunderstandings is not accidental. The human mind is naturally drawn to narratives that preserve possibility. The idea that there are alternate versions of oneself somewhere can soften regret. It can suggest that no decision fully closes off other outcomes. This psychological comfort helps explain why multiverse themes spread easily in popular culture. Cognitive science shows that humans regularly engage in counterfactual thinking. We simulate alternative pasts and futures as part of learning and decision-making. Imagining different outcomes strengthens planning and emotional processing. When fiction externalizes these simulations into literal alternate worlds, it transforms an internal cognitive process into a visible universe. This does not mean that popular portrayals are meaningless. They reflect genuine psychological patterns. Stories about alternate selves allow audiences to explore identity from multiple angles. They make abstract questions about choice and consequence tangible. The appeal lies less in physics and more in emotional resonance. Maintaining a clear distinction remains important. Scientific multiverse models arise from mathematical reasoning about inflation, quantum theory, or infinite space. Popular culture uses the multiverse as metaphor, spectacle, or narrative flexibility. Both operate within their own domains. When they are confused, expectations about physics can drift away from evidence. In this sense, modern pop culture does not disprove or confirm multiverse theories. It reshapes them into symbolic language. The scientific question concerns the structure of reality. The cultural question concerns how humans process possibility. Recognizing the difference allows both conversations to continue without merging them into a single misleading story. When the idea of a multiverse enters discussion, one question rises almost immediately. Can it be tested? Speculation, no matter how elegant, does not become science without some connection to observation. Physics advances not only by imagination, but by measurement. If multiple universes exist beyond our observable horizon, the challenge is not to describe them poetically, but to ask whether any trace of their existence could appear within the region we can see. In inflationary cosmology, the possibility of bubble universes arises from the idea of eternal inflation. If inflation continues in some regions while ending in others, then our observable universe could be one bubble among many. The immediate difficulty is separation. Other bubbles, if they exist, would lie far beyond our cosmic horizon. Light from those regions has not had time to reach us. The space between bubbles expands rapidly. Direct observation is not expected. Yet some cosmologists have asked whether indirect evidence might be possible. If bubble universes formed close enough to one another in the early stages of inflation, they might have collided before being carried apart by expansion. Such collisions, in principle, could leave imprints in the cosmic microwave background. These imprints would not resemble galaxies or stars. They would appear as subtle irregular patterns in the radiation that fills the sky. The cosmic microwave background, often abbreviated as CMB, is a faint glow left over from the early universe. It represents radiation released approximately 380,000 years after the Big Bang, when atoms first formed and space became transparent to light. The CMB is remarkably uniform, but it contains tiny fluctuations in temperature. These fluctuations are measured with extraordinary precision and provide information about the universe's early conditions. If a collision between bubble universes occurred before the CMB was emitted, it might disturb this uniform pattern. Theoretical models predict that such a collision could produce circular or disk-like anomalies in the temperature distribution. Researchers have therefore searched CMB data for unusual circular features that cannot be explained by standard inflationary fluctuations. Data from satellites such as WMAP and later Planck have been analyzed with this question in mind. The Planck satellite, launched by the European Space Agency, provided the most detailed map of the cosmic microwave background to date. Its measurements of temperature fluctuations and polarization patterns allowed cosmologists to test subtle predictions of inflationary models. Some studies have claimed to identify possible anomalies, regions where the temperature variations appear slightly unusual. However, identifying a statistical anomaly does not automatically imply a bubble collision. The early universe was filled with random quantum fluctuations amplified by inflation. These fluctuations alone produce patterns that sometimes appear structured by chance. Distinguishing between random variation and genuine collision signatures is extremely difficult. The search for bubble collision evidence, therefore, becomes a question of probability. How likely is a given pattern to arise purely from standard cosmological processes? Does adding a bubble collision model improve the fit to the data significantly? So far, no anomaly in the CMB has reached the level of confidence required to confirm a collision. Patterns that initially appeared suggestive have generally fallen within expected statistical variation once analyzed more rigorously. Another line of investigation concerns polarization patterns in the CMB. Inflation predicts the existence of primordial gravitational waves, ripples in spacetime produced during the rapid expansion of the early universe. These waves would leave a distinctive signature in the polarization of the cosmic microwave background, known as B-mode polarization. Detecting such polarization would provide strong evidence that inflation occurred. In 2014, the BICEP2 experiment announced that it had B-mode polarization consistent with primordial gravitational waves. The announcement generated significant excitement as it seemed to support inflationary theory strongly. Because eternal inflation extends from inflationary models, such a detection was viewed by some as indirect support for broader multiverse scenarios. However, subsequent analysis revealed that much of the observed signal could be explained by interstellar dust within our own galaxy. When Planck data were combined with BICEP2 results, the interpretation shifted. The evidence for primordial gravitational waves became less certain. What initially appeared as confirmation turned into a reminder of how delicate cosmological measurements can be. The BICEP2 episode illustrates an important aspect of testing multiverse-related ideas. The chain of inference is long. Detecting gravitational waves from inflation would support inflationary cosmology. Eternal inflation is one extension of inflation. Bubble universes arise within some eternal inflation models. Each step adds complexity. Evidence for one component does not automatically verify the entire structure. Beyond bubble collisions and gravitational waves, researchers have explored whether large-scale anomalies in the universe's structure could hint at influences beyond our horizon. For example, unusual alignments in the CMB multipoles or unexpected asymmetries in temperature distribution have been examined. Yet these anomalies remain controversial. Statistical significance fluctuates depending on the analysis method. The difficulty lies in the nature of cosmological data. We have access to only one observable universe. Unlike laboratory experiments, we cannot rerun the early universe under slightly different conditions. The CMB is a single realization of underlying statistical processes. Extracting rare signals from this single dataset is inherently challenging. Some theorists argue that even if bubble collisions occurred, their signatures might be too subtle to detect with current technology. Others suggest that the probability of a collision affecting our observable region could be extremely low. In many eternal inflation models, bubbles are separated rapidly, making collisions rare events from the perspective of any given observer. It is also possible that certain versions of the multiverse leave no observable traces at all. If other regions are entirely causally disconnected from ours and never interacted during the early universe, then no signal could propagate between them. In such cases, the multiverse would remain a theoretical consequence of underlying equations rather than an empirically testable entity. The search for evidence therefore proceeds cautiously. Researchers develop statistical tools, refine measurements, and compare models against data. Planck's high-resolution maps continue to serve as benchmarks for cosmological testing. Future missions may improve sensitivity further, searching for faint polarization patterns or subtle irregularities. At present, however, no observation has provided definitive evidence for other universes. No circular pattern in the CMB has been confirmed as a bubble collision. No polarization signal has conclusively verified primordial gravitational waves at the level required to establish eternal inflation beyond doubt. The data remain consistent with standard inflation without requiring additional universes. This does not mean the multiverse is false. It means that evidence, as currently available, does not compel its acceptance. The distinction matters. Science does not advance by proving possibilities wrong simply because they lack confirmation. It advances by measuring carefully and acknowledging uncertainty. In this sense, the question, can the multiverse be tested, remains open. Some models predict observable traces. Researchers continue searching for them. Others may remain beyond empirical reach. What can be stated clearly is that so far, no experiment or observation has produced decisive proof of multiple universes. The multiverse, if it exists, has not yet announced itself in the sky. It remains a hypothesis emerging from theoretical extensions of well-tested models. The cosmic microwave background has been examined with extraordinary care. Its patterns are intricate and informative, but within those patterns, no unmistakable signature of another universe has been found. For now, the search continues quietly. Data accumulate, analyses refine. The possibility remains mathematically coherent. Yet the evidence remains incomplete. And in cosmology, patience is often as important as imagination. Scientific ideas gain strength not only from elegance, but from limits. A theory is not considered scientific simply because it is imaginative or mathematically consistent. It must also meet certain criteria about how it relates to evidence. When discussions turn to the multiverse, these boundaries become especially important. The question is not only whether multiple universes could exist, but whether the claim belongs within the domain of science. One of the most influential figures in shaping modern ideas about scientific boundaries was Karl Popper. Popper argued that scientific theories must be falsifiable. This means that a theory should make predictions that could, in principle, be proven wrong by observation. If no possible observation could contradict a claim, then the claim falls outside empirical science. It may still be meaningful, but it occupies a different category. Applied to multiverse models, falsifiability becomes a delicate issue. Some versions of the multiverse arise as consequences of inflationary cosmology or quantum mechanics. If those underlying theories make testable predictions, then the multiverse may be indirectly connected to observation. However, if additional universes are completely causally disconnected from ours, then they may produce no measurable effect. In that case, the multiverse becomes a theoretical extension without direct empirical access. This does not automatically disqualify the idea. Physics often works with entities that cannot be observed directly. Quarks were accepted before they were individually detected because the theory predicting them made successful testable predictions elsewhere. The important distinction is whether a theory, as a whole, remains tied to observable consequences. A multiverse emerging naturally from a testable framework may inherit scientific credibility from that framework. Critics argue that certain multiverse proposals risk weakening explanatory standards. If any observed physical constant can be explained by saying that it simply varies across countless universes, then explanation may lose predictive power. Instead of predicting specific values, a theory might only say that we observe what is compatible with our existence. This line of reasoning is sometimes associated with anthropic arguments. While such reasoning can be logically consistent, it must be handled carefully to avoid circular explanation. Supporters respond that rejecting the multiverse purely because it feels expansive may also be premature. If the mathematics of well-tested theories leads naturally to multiple domains, then ignoring that implication would be selective. The debate therefore centers not on imagination, but on methodological discipline. How far should theoretical extrapolation be allowed to go beyond direct observation? In contemporary academic discussions, the multiverse is neither universally accepted nor dismissed outright. It is treated as a serious but speculative extension of existing models. Researchers continue to examine whether observable consequences might emerge, especially within cosmology. At the same time, many physicists emphasize caution, reminding audiences that theoretical consistency does not equal empirical confirmation. The tone within the scientific community is generally measured. Few researchers claim that the multiverse has been proven. Equally few declare it impossible. Instead, the discussion remains conditional. If inflation behaves in certain ways, if quantum mechanics is interpreted in certain frameworks, then multiple domains may follow. Each if carries weight. Each depends on ongoing theoretical and observational work. The multiverse occupies a careful boundary within science. It emerges from mathematical frameworks that successfully describe inflation and quantum mechanics. Yet its broader implications often extend beyond what we can currently observe. This tension raises important methodological questions. Following Karl Popper's idea of falsifiability, scientific claims should, in principle, be testable or capable of being proven wrong. Some multiverse models remain indirectly tied to observable predictions, while others may lie permanently outside empirical reach. The distinction matters. For this reason, the prevailing academic tone is measured rather than dramatic. The multiverse is not treated as established fact, nor is it dismissed outright. It is regarded as a speculative extension of otherwise successful theories. The appropriate stance is patient and disciplined, open to evidence, cautious with interpretation, and aware that theoretical elegance does not replace observation. In that balance between imagination and measurement, cosmology continues its work,